So here we go with some more work and energy type stuff. So in this situation here we have a 75 kilogram person falling, and they're going to land on a giant blob of jello, because if you had the chance to fall into a giant blob of jello, wouldn't you do it? I would. So anyway, so he's going to fall, and he's 75 kilograms, and let's say he goes and he falls, let's say 16 meters. So it's a pretty far distance. So we're going to find out a couple things. So first of all, we are going to find out how fast is he going when he actually hits the jello. And the second thing we're going to find is, let's say he goes into the jello, and let's say he goes in, I don't know, let's say he goes in 60 centimeters or 0.6 meters. So what force actually stopped him when he hit the jello? Okay, well, let's see if we can piece things together. Well, if we start at the very, very beginning, and we'll use work and energy for this. If we start from the very, very beginning, when he started out, he had gravitational potential energy. So up here, he had gravitational potential energy equal to mgh. Now, of course, I have his mass of 75. I've got the 9.81 for gravity, and I also know that he started 16 meters off the ground. So if I punch all that out, give or take, we'll round off, he's got about 11,800 joules of potential energy. So we're just going to take that energy and move it around. So when that energy is down here and he hits the jello, it is all turned into kinetic energy. So it's all kinetic energy when he hits the jello. And of course, all that is taken away by work when the jello slows him down. So we'll use those two things to figure out our values. So first of all, if I try and find out the speed that he hits at, I'm just going to take that potential energy, the total energy started with, that 11,800, I'm going to make that equal to just his kinetic energy. Now, of course, you could have done mgh is equal to 1/2 mv squared right away and canceled off the m's, because mass has nothing to do with how fast you fall, so it's irrelevant, but that's okay. Now, if we just sort of equate those two, 11,800 is equal to 1/2 mv squared, I can then solve for my v. So I've got my 11,800 for my joules. I'll just times that by 2, and then divide that by the mass of 75, and then don't forget to square root your answer. And we'll find out he's going around 17.7 meters per second when he hits the jello. So let's see how far he goes into the jello and how much force was used. So I'm just going to take that exact same energy, the 11,800. That's how much potential he has. That's how much kinetic he had when he hit the jello. And therefore, that is how much work the jello will have to do in order to actually stop him. Now, of course, as he goes down, he's going to have a little bit more work done by gravity. We're not going to worry about that. We'll just ignore that for now. We're just going to get a general idea what's going on. So he hits with 11,800 joules of kinetic energy. So that's how much work the jello has to do to stop him. So the jello has to take away all of that energy by doing work on him by applying a force over a distance. Well, I know the distance is 0.6, so now I can calculate the force that was used, and it would be an average force, because, you know, work equals FD, use a constant force or an average force, and obviously if you hit the jello, it's not giving the same amount of force as you go into the jello. So this would be the average force, which is fine. So I've got the 11,800 joules of energy. We're going to divide that by the 0.6, and then we get a force of approximately 19,700 newtons of force is actually being used to stop the person when they hit the jello. And that would be the average force. So now let's build on this situation a little bit. Suppose this 75 kilogram skydiver, so to speak, has a buddy, and the buddy is coming along and is going to try and help by trying to catch the person. And for some reason they don't notice the jello, but they are going to try and catch the person. And of course, they're not paying attention whatsoever to where they're running, because they're looking up at their friend, and maybe they are also texting on their phone at the same time, so they have no idea that the jello is there, and they are running in at, let's say 5.6 meters per second, and they're going to run into the jello. Well, let's see how far into the jello that person would go, assuming the exact same force is being used to stop them. Now, let's say this person is 82 kilograms. All right, so let's see how much or how far they would go into the jello if they actually hit it. Now, this person, of course, has kinetic energy coming into the situation, so we can find their kinetic energy. If I find their kinetic energy, that'd be 1/2 mv squared. So we've got the 1/2, we've got the mass of 82, and we've got the speed of 5.6. And again, don't forget to square the 5.6. And we get a kinetic energy of about 1290. So 1,000, erase that, 1,290 joules of kinetic energy. So that is how much work the jello will have to do in order to stop them. And we'll assume it's the exact same force. Both guys going into the jello, blah, blah, blah. So we'll assume it's the same resisting force. So with that idea, I can then solve for the distance. The work done by the jello would be 1290, because it's got to take away all the kinetic energy. And we will divide that by the force, and we'll use the exact same force as over here. So we've got the 1290 divided by the 19,700. So we got the 1290 for the energy. We divide that by the 19,700, and we get a distance of, well, just about 6.5 centimeters. So about 6.5 centimeters or 0.065 meters. Obviously, they're not going to go nearly as far in because they're not going nearly as fast as the skydiver. So let's build on this a little bit more. Let's find out what was his speed. How fast was he still going 3 centimeters into the jello? Okay, so he's going into the jello 3 centimeters, and obviously still going, so it's about almost halfway there. But let's see how fast he was going when he was 3 centimeters in. All right, well, the kinetic energy started with hasn't changed. He's still starting with 1290, but as he goes in, the jello is going to do work on him, which is going to be force times distance, and that would be 3 centimeters. And we can find out how much work was done on the runner while he's going into the jello. So we've got the average force. That still hasn't changed. That's still 19,700. And we'll just keep it nice and constant to make things easy. We'll multiply that by the distance of 3 centimeters. Make sure you convert that into meters. And we can see that the jello would have done about 591 joules of work to slow him down. So this is energy that is lost to the jello. So it came in with 1290. Jello did about 590 joules of work on him to slow him down, which means we can subtract the two to find out how much energy he actually has left. Okay, so the remaining kinetic energy will be the difference between the two. So the kinetic energy that he has left is going to be the 1290. Take away the 590, which is around, well, so let's say 700 joules. So he's got 700 joules of kinetic energy left. We can make that equal to 1/2 mv squared, and then we can just solve for the new v, and we can find out how fast he's going. So we can times that by, or times the 700 by 2 for the 1/2. We divide that by his mass of 82, and then we can take the square root, don't forget to square root, and we can find out how fast he's going. And obviously he's going less than 5.6. And if we do solve for this, we get about 4.1 meters per second. So he's still going about 4.1 meters per second after he's gone into the jello about 3 centimeters.